algorithm. Secondly, it is from the availability of massive training data through the internet. And thirdly, it is because the progress of energy efficient computing through the progress of the semiconductor technology. The major milestone of AI advances, together with the leading edge semiconductor technology innovation at the time. For example, the Deep Blue supercomputer was implemented with 0.13 micron technology. The initial image recognition by deep neural networking was implemented with 45 nanometer technology. The famous AlphaGo was implemented with 28 nanometer technology. An initial ChatGPT server for training was implemented with 5 nanometer technology. I think you should all be very proud of this. Recent ChatGPT is powered by server using our 4 nanometer technology. ChatGPT has found its use in many applications in everyday life. It is a good example of how AI has democratized the usage of high-performance computing, providing benefits to every individual in the society. The computation and memory access required by these AI training have increased by order of magnitude in just past 5 years. Training a GPT-3, for example, requires more than 5,000 petaflop days, or 5 times 10 to the 18 flop days of computation, and 3 terabytes of memory capacity. Both the computing power and the memory access required for generative AI application are still growing very rapidly. We now need to answer a pressing question. How can semiconductor technology advance at such a fast pace? Since the invention of the integrated circuits, semiconductor technology have been about scaling down in feature sizes so that we can cram more devices or transistors into a thumb-sized chips. Today, the integration has been one level higher. We are now putting together many chips into a tightly integrated, massive interconnected system. This is the paradigm shift in semiconductor technology integration, which we have been witnessing for more than a decade though. We're now going beyond 2D scaling into 3D system integration. In the era of artificial intelligence, the capability of a system is almost directly proportional to the number of devices or transistors being integrated into this system. Using an interposer, we can extend the size of the integrated system beyond the lithographic reticle field size. We can integrate a system that contains a much larger number of devices that is possible on a single chip. For example, here shows the supercarrier interposer under development based on CoWoS technology. It will be able to accommodate up to 6 reticle size for those computing chips, along with 12 HBM3 memory cubes. The other key technology gets increasingly important for artificial intelligence is 3D SOIC. Here is an example how this SOIC technology can do for the future 3D stacked DRAM. Today, the conventional high bandwidth memory relies on through silicon vias and solder bumps. TSMC's 3D SOIC technology can provide a bumpless alternative to the conventional HBM technology today. In this HBM test structure, there are 12 layers stacked face to back, bounded at low temperature on top of a large base logic chip. The total thickness is only 600 micron. The integration of multiple chips, either by CoWoS or SOIC, allow the total device or transistor count on a system to be much larger than one can squeeze into a single chip. Typical GPU chips using for AI training have already achieved the radical field limit, and their transistor count is about 100 billion transistors. The continuation of the trend, increased transistor count, will require the computation to be performed by multiple chips, interconnect with 2.5D or 3D integration. We forecast within these decades, multiple chip GPU will compose of more than 1 trillion transistors. Through interconnect pitch scaling and in many of your equipment suppliers' help, there's plenty of room for large SOIC interconnect counts that we use today. So how do all these innovative hardware technology contribute to the performance of a system? This slide shows the trend of energy efficient performance for the server GPU. Over the past 15 years, our industry has increased energy efficient performance by about 3 times every 2 years. This trend will surely continue in our historical rate. It will be driven by innovations from multiple sources, including new materials, device and integration technology, EUV advances, DTCO, design technology co-optimization advances, circuit designs, and system architecture design. In particular, the energy efficient performance increase will be enabled by the CoWoS and SOIC advances. Moreover, concepts such as system technology co-optimization will become increasingly critical. There are NVIDIA Ampere and Hopper GPUs. Each consists of 1 GPU die with 6 HBM cubes on a silicon interposer. Transistor count for Ampere is 54 billion transistors, and Hopper is 80 billion transistors. From TSMC's N7 technology to the denser N4, we managed to increase about 50% more transistor essentially on the same area. These Ampere and Hopper are the workhorse today of large language model training. We need tens of thousands of these processors in a server to train ChatGPT. My last example is arguably the largest chip to date from Cerebras. The die size is essentially the size of a 300 millimeter wafer and contains 2.6 trillion transistors at TSMC's 7 nanometer. The innovative idea here is to add interconnect across wafer scribe lines to connect many computing cores. The key message is here. There will be technology beyond CoWoS and SOIC, and we are very excited to unleash innovation by working very closely with our customer. With a high-performance computing system composed of large number of dies, running large AI models, high-speed wire communication may quickly limit the computation speed. Today, optical interconnects have already been used to connect server racks in data center. We will quickly come to a need that optical interfaces be packed together with GPUs and CPUs. This will allow energy and area efficient scaling up of bandwidth for GPU to GPU communication, such that hundreds of servers behave as a single giant GPU. In this area, TSMC's compact universal photonic engine technology will play an important role using SOIC, bonding electronic and photonic blocks right next to the GPU and router switches. So fueled by AI algorithm, silicon photonics, technology will become a key technology of this industry. In 1980s, still remember Professor Carver Mead and Professor Lin Conway of Caltech invented a computer-aided design method for integrated circuits. They use a set of design rules to describe the chip scaling process technology, so the circuit designer can easily design VLSI circuits without much knowledge about the process technology. Today, in the 3D IC world, the design part includes now VLSI designs, system architecture design, and software-hardware optimization. And the process technology part includes the chip scaling technology, 3D IC technology, and advanced packaging technology. Again, we need a description language to define the said technology and convert it to an EDA technology file for designer to design 3D IC circuits. This is exactly the purpose of the recent initiated TSMC 3D blocks, a hardware description language to describe various 3D IC technologies using common interpretation standards. This gives designer a free hand to work on 3D IC system design, regardless the underlying 3D IC technology from which company. This 3D IC blocks have already been embraced by most today's technology companies and EDA companies. In summary, in the era of artificial intelligence, semiconductor technology is a key enabler for new AI capability and application. A new semiconductor product is no longer restricted by the chip size of the standard form factor. A new semiconductor product is no longer limited by the scaling of the next generation technologies. An integrated AI system is composed of a maximized number of energy-efficient transistors, an efficient system architecture for specialized compute workloads, and an optimization of software and hardware. So for the past 50 years, the semiconductor technology development has been felt like walking inside a tunnel. The road ahead was clear, and there was a well-defined path. Everyone knew what need to be done, shrinking the transistors. Now we are reaching the exit of this tunnel. Semiconductor technology gets harder to develop, yet beyond the tunnel, many more possibilities lie ahead in the future. We are no longer bounded by the confines of the tunnel. Thank you for your attention. Thank you.